Hello, and welcome to lecture number 2 on recursion. Right now we're going to look through 2 examples to hopefully give you a better understanding of why recursion is useful and why recursion can let us do something that for loops can't do. All right, so let's go to recursion, part 2. So we're going to look at nested data structures and recursion. So nested data structures require us to do things that we can't implement with a for loop. Then we'll look at nested arrays and nested objects. So, like many other languages, JavaScript can have very deeply nested data structures. And what does that mean? It just means data structures inside of data structures, right? So for example, we have a crazy array, and this array is, you'll notice here, it's an array of an element. The first element has just 2 items, right? The item 1, and then the second item being this array, which each array only has 1 item in it, right? All the way down to an array of 1, and before you see we're closing all these arrays. So it's really, each array only has 2 things. But then because that second thing is an array, it's really a very deeply nested structure. So if you wanted to iterate through all the elements in this array, you'd have to in essence write 9 for loops, right? You say, for everything in this, go through here, and then for i equals 0, I less than the length, and then if I is, if that thing's an array, for j equals 0, j to the length of the array, all the way down until you're either out of alphabet letters or, driving yourself crazy. You have 9 nested for loops. And then all of a sudden, someone could very easily add, change this 9 to a 9 comma bracket array 10, and then you'd be back into, you have to rewrite your whole code again because now you would need 10 nested for loops, right? So you can't define this problem in a way that is solvable with just iteration. So here's why recursion is really a great tool to iterate through these nested data structures, because recursion is great at solving a problem if you can define part of that problem as a subproblem of the same type, right? So if you don't know how many levels of nesting, recursion can help you here and let you handle as many levels as you need down to your base cases, right? So for example, let's say we want to log an array like that, right? So we have a nested data structure of an arrays, and let's start with making sure that we can log a flat data structure, right? So logs an array, takes an array, it uses a for loop to go through that array, and sets the element to the array I, and then console logs that out, right? So if I log an array of 1, 2, 3, I should expect just 1, 2, 3, one after the other, right? Like so. Now, what if I want to try to log an array that looks like this? An array with element 1, second element being another array of 2 and 3, right? So here's a question is that on line 3 of the code, we have to think, well, element can either be a number or it can be another array, right? So now element can be one of 2 things, right? Because the array has both numbers and array elements in it. So what we have to do is think, if element is an array, we want to log every number inside of that array. Now, here's where we start seeing the beauty of recursion, right? Because we have a problem, right? We're going through an array and we say we want to log every element of this array. We just came upon an element that is an array where we also want to log its numbers. The beauty of this is that we already have a function that does that, right? We already have a function that logs out all the numbers of an array. So this is what we get right here, is that we would get, before we fix this, we would get 1, that would be logging out the 1, and then console log of the second element would give us an array of 2, 3. But that's not what we want. We want 1, 2, and 3, right? So let's modify logs an array to look at that. So here, we say let element equals to the array at the index, and if the element is an array, then we log an array, else console log the element, right? So if element is an array, we can just call ourselves again, because we know that what we do is output arrays that have either numbers or other arrays, right? So now if we do logs an array, we'll get what we want here. First we call logs an array with 1, 2, 3, and that outputs 1, right? Because the first time we go, the if check fails, right? Because where the element is not an array, and we console log out the 1. But then the second time we go through, we get called with a 2, 3, and then 2, 3 will pass the first if statement on line 5, and then that will log out 2 and 3, and then return. All right, so let's do that example in a code snippet. So open up VS Code here. Okay. So here, okay, so we want to, let's create an array. My array equals 1, and then a nested 2, 3. And then we'll have a function that logs an array, takes an array. And what this function should do is log out all numbers, even ones nested in other arrays, one line at a time. Right? So what we should do here is we want to go through all the elements of this array. For let I equals 0, I less than the array dot length, I plus plus. We want to say, okay, if this is an array, and this function, it comes from JavaScript itself, if this is an array, and a lot of times people will do I, right? But I is not correct here. I, of course, will never be an array. I is the index. So to be more explicit, we can say let element equal to array I, right? So the element here will be the 1 or the array 2, 3. So if this is an array, this element, then we do, this is the recursive case. Else, this is a number, and this is kind of like, you consider this like a base case, right? This is, we have this, we don't have anything else to do with this, so let's just output it. And then the recursive case, what we want to do is just call ourselves, right? Logs an array. Well, okay, if we didn't have recursion, what we have to do this is for let j equals 0, j less than element.length, j++, and then console log element j, or sorry, element I, sorry, element j. Right? And then, of course, this for loop would have the same problem, right? We would do something like if element j, or if, array.isArray element j. So you see, this, it never ends, right? So we don't need to repeat the code because we already have something that can do the code for us. We can, in the recursive case, just do something like this. Logs an array of element, right? Because we know element here is an array, and we already have a function that can take an array and log all of the elements nested in it. So if I run this, let's see. Okay, var command not found. Okay. All right, and so it is going, so it is running. Now, of course, we have to call the function. And let's see what happens. All right, we're getting 1, 2, 3, one at a time. And now you can see here, if we made this thing, instead of singly nested, we made another level. Let's run it again. Logs and array continues to work. It can handle deeply nested structures, right? Whereas if we had done it with a for loop, now our code would break. Our code would look something like, our code would show one of the levels, any level below what we had hard-coded into it, it would show with the brackets, because console log knows how to output an array, but doesn't know how to output all the individual elements of that array. Okay. So let's look through another example of, let's say we want to concatenate all the elements of the array together. So again, in the last example, we were just doing something inside each level of the recursion. Now, what if the levels of recursion have to send something back up the chain, right? Then it gets much more complicated. It's the second thing of, well, what are the base case communicating up the level, and how are those things communicating up, or how are things communicating up the call or down the call stack, right? As the call stack unwinds, what do we have to send back up the chain? So here, concatenate elements, it says, I want to take all of the things inside of an array and put them into one string. Okay, so we'll create a string called an empty string, and then we'll go through the array length, and then for each element, we're going to add it to the final string, and then return the final string, right? So if I concatenate the elements of an array of A, B, and C, of all those are strings, what I should expect is A, B, C, right? I concatenated A and concatenated B, concatenated C. And again, concatenate just means join to the end of. All right, so now let's look at this here. Now, what if we want to concatenate things that are nested, right? We have, again, the same thing that we do. Now we have the element. We say, well, is this the element an array? And if so, we add it to the final string, concatenate the elements. Otherwise, we could just add the string itself. So here, we have both the normal case, which is just adding a regular string, and we have the case where we're adding the results of a recursive case, right? So we come upon an array and say, you know what? This is an array of strings I want to concatenate to myself. I don't know how to concatenate an array of strings, but I know a function that can concatenate all the strings underneath. And then once you're done concatenating, return me the string that you've concatenated, and I will add it to the string that I'm managing. So one thing that's kind of tricky here is that final string is not the final string that you're returning to the user necessarily, because each level of recursion is dealing with its own final string, right? So each level of recursion sees only its world. It says, like, my final string is just the array I was given. I'm returning that, and someone else might use it to build an even larger final string. Right, so here, if I set concatenate elements to A, comma, and then another array of B and C, what will happen is that the first time, final string will be A, and the second time, I'm going to recurse into the array of B, C, and then for each of those elements, I'm going to get B and C put together, and then come back up, and then the concat_else will return BC and add it to the A in final string. So here, let's do an example. We call concat elements with the full array. The final string here is empty, and then it gets added. It gets A added to it, so now it's A. Now this is line 6, where we're getting to the second element, and now final string is A, and final string is being added to a call to concat_else with B and C, right? So now we've called concat_else, so we're going to add another function to our call stack. Now concat_else of B and C, what does that do? Its final string starts as empty. Now it's starting to go through the loop, right? So first we add on line 8. Now line 8 of the recursively called concat_else, right? We add B, and then again we go through the loop, and now we get C. So now concat_else final string is BC, and it's going to return that up the chain. And here we can look at, when concat_else returns off of the call stack, you replace concat_else in this function with what it returned, right? So it's BC, and then this becomes BC here. And then now we're back in the higher level of concat_else, and we're on line 6 in the top level concat_else, where concat_else, the function call on line 6 has become BC, and it's being added to A, the final string, and we get ABC. Right? And then that's returned to the user, so we should expect ABC. All right, so that's looking at arrays, how we can nest into the arrays, and we can have infinitely nested array structures that would only be handleable with recursion. Right? If we use for loops, we just can't handle for loops that deeply unless we wrote out all the for loops. But then again, not only would that be inefficient and hard to manage, but it would still fail if we got to an array structure that was too deep. So it's just not the way to handle it. The only way to handle it is with this, with using recursion to solve the subproblem of what would I do when I'm navigating through my array and I encounter another array like myself, right? That's a perfect example of recursion of how do I solve this problem, and I can define that problem as parts that I can solve, my base cases, and then subproblems that I can solve, using a recursive case. Okay. Let's talk about nested objects. So nested objects are very similar to nested arrays, right? Nested objects just means that you have a JavaScript object where a key can have a value that might also be an object, right? Instead of using a normal for loop, we can use a for in loop to iterate through the object. And if the value is another object, just recursively call the function on the nested object. So let's look at sum vals, right? So what sum vals will do is just sum all the values in an object. So we have an object of keys and values, and let's say those values are numbers, and we want to add up all the numbers in our object. For example, let's say the keys are different classes, and each value is a number of students. We can add up all the keys to get the total number of students in our school. So here's a function. We'll create a sum 0 for all the keys in the object, get the value, and then add the sum to the value, and then return that sum. So here we've written the base case where we only handle objects that have values and no objects as values, right? So this is only where we have numbers as values, not objects as values. So here, if we call sum vals on an object where, let's say we have two key value pairs, one A, key A value 10, and one key B value 20, what we'll do here is, we console log it, we'll get the value 30 because we'll go through, the for loop will say the first one key will be A, we'll get value 10, add 10 to 0, we'll get 10, and we'll go through again, we'll get key is B, object key will be 20, and then add 20 to sum to get 30. Okay, now let's assume that we can support objects instead of just numbers in our key value pairings, right? So here we again get let value equals object key. Now we say, well, if this value is an object, we have to do the recursive case. We can't just add it to our sum because adding an object to a sum is ill-defined, right? So we say, but we have something that can do this already, right? So we just say, take the sum and add it to a recursive call to ourselves, a recursive call to sum vals, passing in that nested object. And then, of course, we have to handle the normal case where we just add the value if the type of value is just object. And then we return the sum. So here, if we add a sum vals of an object with A1, B being an object, with C being an object, D being an object, E having value 2, F having value 3. So A has the value 1 at the top level. Then we have B going to C, going to D, going to E, and F with 2 values, right? So we should expect the value 6, but we have to do quite deep of nesting. So here, let's look at the call stack, and we can look at each level. So we'll start with sum vals of the whole thing. Sum is 0. Then we add 1, right? Because the first thing we get is A, and A returns us the value of 1. And then we're going to do the next object, which is sum vals of the object with key C, right? So we call this sum vals of key C. Well, the sum is 0, but C doesn't return a value. C's type of value is object. So again, we call sum vals of the nested object. Then again, sum vals of D. D key is also the value is object. So we again call sum vals of E of the nested object with E and F. And then finally we call sum vals of E with just the object E and F. And here we get plus 2, 2 plus 3, we get 5. And so then sum vals becomes, sum vals of E2, F3 is 5. Again, we replace that at the higher level with the expression. We replace the sum vals function call with the value that it returned. So we get 0 plus 5. Then we get 0 plus 5 again. And then finally we get 1 plus equal to 5. That returns 6. And then that is what returns to the result. And we get console log of 6. So again, it's the same idea that we just did with concatenation. We're passing up the value each time until we hit a base case. Our base case here being when we find an object that has no key value pairs where the values are also objects, right? So in this case, the object right here with E2, F3 is our base case because it has no more values that are also objects. All right, so this was a short lecture. We talked about a really good use case for recursion, which is navigating nested data structures, right? Because nesting can go infinitely deep. In theory, I mean, in practice, you might see nesting all the way up to 5, 6 levels. For example, things like a menu bar system, right? On Amazon, you click all categories and it shows all these things that expand all this way down, right? You want to have a recursive function that can display that out. So like, if someone adds a new category that has a new subcategory, Amazon doesn't have to redesign the whole menu system. Another place we see this is, if you want to output a value as JSON, that's a great use of recursion, right? Because JSON is, in essence, doing what we did with concat elements, concatenating into one big string a JavaScript object, right? So if you want to write your own JSON stringifying function, then you would use recursion to say, well, for each element, or for each key value pair in my object, let me say, is this a nested data structure? And if it's so, call myself again to handle this nested data structure. And then we look at handling nested arrays and nested objects. And typically when we think about the recursive, we think about in the kind of pure recursive terms, a nested arrays and nested objects, we think, okay, what is the base case? And the base case here will usually either be an empty object, or an empty array, or an array with one element, or an object that has no nested objects in it. So those are our base case. And recursion is really just passing the nested object back to ourselves, right? Because what we're doing in our recursive function is handling the object, and then when we see another object like ourselves, we pass that to ourselves to get whatever value that is coming out of it. All right, so that's a brief intro to recursion. Again, I want to emphasize that recursion is an elegant technique that can be used to solve problems, a wide variety of problems that are hard to solve in other ways. But these problems aren't things that you'll come upon a ton in your early programming. In fact, the number of times I've actually used recursion in web programming in the last 10 years, I can probably count on 2 hands, right? And so oftentimes it's, there's oftentimes an easier or simpler way to do it than writing a recursive complex function. Now, in coding competitions, sometimes in job interviews, recursion becomes more important, but that's something that we'll study a lot, or you'll study a lot, in an immersive program, or once you get to that point where you're ready to start studying for job interviews. But right now, as you're thinking about just getting to learn how to code, you should know that recursion is there, what it's used for, and when you see problems like this, you say, oh, okay, that might be a recursive problem, but don't feel like you have to be able to solve it right away. It's a technique that takes a while to get used to. It's one of those things that many, many early students in computer science struggle with for a long time. So if the last 2 lectures you're a little bit like, I'm not really getting what's going on here, I kind of see how to do it with the examples that was shown, but I don't really understand how to do it again, that's a perfectly fine place to be. And in fact, if you don't even get those examples, that's an okay place to be. I think you'll get a lot out of working on these problems and exploring different ways of looking at things in a recursive way. All right, thanks so much, and see you next.